Okay, welcome everyone, and how are you doing? Alright, so I'm excited because we are going to move into a new chapter, chapter 4, which is one of the core chapters in this differential equation course, one of the most important chapters in this course. Okay, in chapter 4, what we are going to learn is how to solve higher order differential equations, specifically second order differential equations. Now we do another specification, which is how to solve linear second order differential equation. So that is the goal of chapter 4. But chapter 4 section 4.1 lays the foundation for that task. Now we have to have a good foundation, and we need to recall few things from what we have learned before. Okay, so let's move on to that. Now I said we are going to only solve linear differential equations. So let's recall what is linear at first. Remember, what is linear? Linear means three things. What are the three things? First thing is, we talk linearity with respect to dependent variable and its all derivatives. Okay, so dependent variable is y and its derivatives, they should be all of degree 1. Power of them should be 1. The number of times that you have taken the derivative, that doesn't matter. Okay, the degrees should be 1. Second thing is, the coefficients of those terms, y and its all derivatives, should be only functions of independent variable, only functions of x. Okay, so here's a perfect model for a linear differential equation. So you can see y to the power 1 dy over dx to the power 1 degree 1, here n minus 1th derivative, but remember power 1. Okay, here nth derivative power 1. So first condition satisfy. Coefficients should be only functions of x, that is why we define them as x, functions of x. Good. The third condition for linearity is that the right hand side function or the non-coefficient function should be only a function of also x. Okay, so if you satisfy those three, like here, you have a linear differential equation, otherwise non-linear differential equation. Okay, so that's the linearity. All right. Second important thing is, we are going to deal with lots of initial value problems and boundary value problems. Now what is an initial value problem means? Again, initial value problem means three things. Okay, what is the three things? How many conditions you need? Nth order differential equation need n conditions. So third order differential equation needs 3 conditions. Second order differential equation needs 2 conditions. Fourth order differential equation needs 4 conditions. So likewise. Okay, so order is equal to the number of conditions. That's the first thing. Second thing is that for if you need initial value problem, the condition should be up to n minus 1th derivative, one derivative less. Remember, if you have a third order differential equation, your condition should be up to second derivative. That means condition for y, condition for y prime, condition for y double prime. That's it. Okay, if you have a fourth order differential equation, you need condition up to third prime, right? So condition for y prime, condition for y double prime, condition for y triple prime, right? So 1 until 1 derivative less, and number of conditions should be equal to order. Okay, good. What is the third thing that you need it to be an initial value problem? All the points, all the x points for all these conditions should be what? Remember, should be the same. It should be, conditions should be at the same x value, same x naught. See? Okay, then you have an initial value problem. How about if you have all these conditions but at different x values? What do we call that? Remember, we call that a boundary value problem. Okay, all right. So if you have conditions for different x values, that's a boundary value problem. Otherwise, it's an initial value problem considering the first 2 conditions satisfied. Okay, so we recall that. The third thing we need is the existence and uniqueness theorem. Probably one of the hardest thing that you have dealt with, right? but it's not hard. Remember, we learned this existence and uniqueness theorem for only first order differential equations, okay? So dy over dx is equal to fxy, only for this type of differential equation. The reason I'm telling this is we are going to learn a new theorem because this theorem, the theorem that you learned previously, does not valid for higher order differential equations. So this is an old theorem that values for only first order differential equations. So let's recall this. This theorem is also three things, right? Oh, well, everything is three things, right? First thing is, function should be continuous in the region that you propose to have a unique solution, or propose to have a guaranteed unique solution. So you look at function f and you pick up the region where f is continuous. Good. And then you look at partial derivative of f with respect to y. This will give a new function, right? So you want this partial derivative of with respect to y to be continuous in the same region, right? If it is not continuous, you choose a different region. So you adjust the region so that f and partial derivative of f with respect to y is continuous. So you need the region, both of them are continuous. Good. Third condition is that your region should include the initial point, initial x value and y value. So the region that's satisfy all these three conditions is the region where you are guaranteed to have a unique solution. Okay, let's do a quick example. So dy over dx is equal to y over x. So f is y over x. So f is not continuous when x is equal to 0, right? So you need a region where x is not included. So you can choose any y value basically. So y, any y value, but x value, that the region that x is not equal to 0. So that is the region that you propose. Second thing, you have to look at partial derivative of f with respect to y. So if you differentiate y over x with respect to y, the answer will be 1 over x, right? Derivative of y is 1. X is a constant, right? Because partial derivative. 1 over x is continuous except at 0, right? So the same region valid, right? So we do not do adjustment to region now. Okay, let's say the initial condition was 1, 2. Okay, when x is equal to 1, y is equal to 2. So you need to choose the region where you have the 1, 2 point. Well, this region, of course, any y value means 2 is also there. Any x value which is not 0 means 1 is included, right? So in this region, you can have a unique, you are guaranteed to have a unique solution for this differential equation. So three things going into chapter 4 is very important. How to find whether a differential equation linear or non-linear. Second thing, what is the initial value problem? What is a boundary value problem? Third thing, don't mix up. This theorem that I explained you is only for first order differential equation. Do not do this for higher order differential equations. For higher order differential equations, we are going to learn a new theorem in the next video. Okay, thank you.